Hello, everyone. We're going to be learning about or practicing combinatorics problems today. And the first problem is this one. So let's start with part A. How many binary sequences of a length at most 5 have exactly 3 ones? All right. So for part A, how many binary sequences of a length at most 5 have exactly 3 ones? So it says at most 5. So we can first break this up into the 5 lengths. There's the length 1 sequences that have at exactly 3 ones. There's the length 2 sequences that have exactly 3 ones. Length 3 that have exactly 3 ones. Length 4 that have exactly 3 ones, and length 5. So how many binary sequences of length 1 have exactly 3 ones? You could shout it out or type it in the chat. So this is not a trick question. There's only one binary value in a binary sequence of length 1. So there can't be exactly 3 ones. So 0. How many binary sequences of length 2 have exactly 3 ones? Okay. So
It would also be 0 as well.
what's that, William? Sorry.
It would also be 0 since there's only 2
Yep.
numbers.
All right. Now, what about how many binary sequences of length 3 have 3 ones?
This would just be 1.
Yep. yeah, there are 3 slots, so it's pretty, it's evident that there's only way to achieve 3 ones here. We would have to put 1, 1, and 1 in the 3 slots. Another way to say that is that amongst the 3 slots, we had to choose all 3. So we can write 1 as 3 choose 3. We had to, so we're choosing slots, and in order to have 3 ones, exactly 3 ones, there was only one way to do that. We had to choose all 3 slots. Okay. How many binary sequences of length 4 have exactly 3 slots? Oh, sorry, have exactly 3 ones, sorry. So
This would be 4.
yes, that's correct. So the idea here is that there are now 4 slots. And what we're doing is we're selecting slots, and we need to select exactly 3 of them to have the ones. It doesn't matter the order that we select the slots in. And we can't select a slot that's already been selected. If we put a 1 in a slot, we can't put another 1 in a slot. So this is the type of selection that we've seen in class. It lacks order, and repetition doesn't. Sorry. It according to the terminology from class, order doesn't matter. Order doesn't matter here, and repetition is not allowed. Doesn't matter, and repetition is not allowed. Repetition not allowed. Okay, so so all we're doing is choosing 3 out of the 4 slots to hold the 3 ones, and we're doing this. We're selecting these slots in a manner in which order doesn't matter, because selecting if we selected this slot, and this slot, it wouldn't matter which order we selected them in. This is just one way in which to have exactly 3 ones. And we also can't repeatedly select a slot. So it's this type of selecting is where order doesn't matter and repetition is not allowed. So if you're thinking about these problems kind of more algorithmically, which maybe isn't the best thing to do, but it's okay. If you are, then you recognize these 2 conditions, and so you know that, oh, okay, this is just using just the combinations. In particular, there are 4 slots, and we're choosing 3 of them. So as William pointed out, this is equal to 4. So this is 4 choose 3. All right. And then the last one follows the same idea. So how many? So it may not be super obvious why 4 choose 3 is 4. There are a couple of ways to think about that. First of all, you can just write out the formula for choosing. So that's 4 factorial over 3 factorial, 1 factorial. So then that's just 4. But you can also think about it a little bit differently. What we're doing is selecting 1 slot to not have a 1. And there are 4 ways to select 1 slot to not have a 1. So 4 choose 3 is the same thing as 4 choose 1. And 4 choose 1 is 4. So, but generally, if you need to figure out the actual number for a combination formula, you'll need to use the the actual formula, which if you don't remember is if this is n and this is k, so we're doing n choose k, that's n factorial over k factorial n minus k factorial. Okay, and then the last one is the number of binary sequences of length 5 that have exactly 3 ones. And so following the same pattern, that's going to be 5 choose 3. So 5 choose 3, if we write out the formula, that's going to be 10. It's 5 factorial over 3 factorial times 2 factorial. And so that's 5 times 4 over 2, which is 10. Okay. So then we add these together to get the final answer. So the final answer is 15 here. Are there any questions about part A? All right, I'm gonna clear my screen. And so before we do part B, I'm just gonna rewrite the answer for part A. It's 15, which is equal to C of 3 choose 3 plus C of 4 choose 3 plus C of 5 choose, or C 5 3. So that'll be just important for the last part of this problem. So, okay, part B. Does anyone have any ideas? You could put it in the chat or speak if you would like to. All right. So this one is actually just like the previous one. Again, we have 6 slots. Now we have 6 slots. 1, 2, 3, 4, 5, 6. And we need to select exactly 4 to be 1. So we're doing, again, we're choosing slots. We can't pick a slot twice to contain a 1. So we don't allow for repetition, and the order doesn't matter. So it doesn't matter if we pick this slot first and then pick these 3 slots, or if we pick this slot first and then those 3 slots. That it wouldn't make a difference. This would still be one way to have. This would still be a single way to have exactly 4 ones. So again, it's a selection where there are no repetitions and the order doesn't matter, and we're selecting 4 from 6. So the answer is C6 choose 4. All right, so then we should just write out the formula to figure out what that is. It's 6 factorial over 4 factorial 2 factorial. Okay, so then in the numerator, the 4, 2, and 3, 4, 3, and 2 are going to cancel. You're going to have 6 times 5 divided by the 2 factorial, which is just 2. So we're going to have 15. All right. So now the last part. Why do these 2 questions have the same answer? I'll give you a moment to think about that, and I'm going to start writing on the board, but just because this one needs a graphic, it's helpful for explanation, but while I'm doing that, take a moment and think about this one. All right. So these are 3 rows of Pascal's triangle. And Pascal's triangle is a nice visual that explains how this choose function, how the values of it are related to each other. So in particular, if you, let's look at an example here. If you take 3 choose 0 and 3 choose 1, then you get 4 choose 1. And this pattern works out everywhere in this picture. If you take 3 choose 1 and 3 choose 2, then you get 4 choose 2. If you get take 3 choose 2 and 3 choose 3, then you get 4 choose 3. And that works out further. So if you take 4 choose 0 and 4 choose 1, you get 5 choose 1. 4 choose 1 and 4 choose 2 is 5 choose 2. 4 choose 2 and 4 choose 3 is 5 choose 3, and so on. So that's a nice little thing. I didn't write out all of the 6th row, and I also did not write out the first several rows just for because of time. So this is missing a couple rows on the top here, so it has this extra triangle part. And that would be like the choosing with the first argument being 2, that would be the second row, and so on. And then for the 6th row, I didn't write it all out, but 5 choose 3 with 5 choose 4, that's 6 choose 4. So the answer to B was 6 choose 4. And this question says, why do these two questions have the same answer? Well, the answer to part A is 3 choose 3 plus 4 choose 3 plus 5 choose 3. So now we're going to use this pattern and how these choose functions are related to each other to explain why part B and A are the same. So we can start off by observing that 6 choose 4 is 5 choose 3 plus 5 choose 4. So 6 choose 4 equals 5 choose 3 plus 5 choose 4. Okay, then we can use that 5 choose 4 is 4 choose 3 plus 4 choose 4. So that's 5 choose 3 plus 4 choose 3 plus 4 choose 4. And 4 choose 4 is the same thing as 3 choose 3. Because there's only one way to choose 4 items from 4 items. That's to choose all the items. Just like there's only one way to choose 3 items from 3 items. So this is 1, and this is the same thing as 3 choose 3. So Pascal's triangle is expressing inequality, which is that C of n choose k is equal to, so we go up to the previous row, so C n minus 1 choose k minus 1, n minus 1 choose k minus 1, plus C n minus 1 choose k, because this is the n minus 1 choose k part, and this is the n minus 1 choose k minus 1 part, and this is the n choose k part. So n minus 1 choose k. Okay. So basically, this is true because of Pascal's equality. And Pascal's equality is what yields this triangle. Are there any questions about part C? All right. Here's the next one. You can take a minute to think about that, and then we'll discuss. All right. So to start, it says we want to rewrite this as a bag problem. So a bag problem, according to our class definitions, that repetition is allowed in a bag problem. Repetition is allowed, but order doesn't matter. Order doesn't matter. Doesn't matter. Doesn't matter. Okay. All right. So that sounds about right for this problem, because we have two prizes which we need to distribute amongst these four people, A, B, C, and D. So if we assign a prize to person A and a prize to person B, that's it says it doesn't matter who gets which prize. So that's the same thing as assigning the first prize to person B and the second prize to person A. We don't care who gets which prize. Only we don't care. Yes, who gets which prize? Only which people get prizes. So A, B, and B, A are the same. So we have this, this order really doesn't matter in this problem. And then repetition is allowed. So a person is allowed to get a prize twice. So AA is possible. Okay. So so this is a bag setting, and a bag setting is equivalent to arranging to the number of ways to arrange items in an unordered list. So we have to figure out two things in a bag problem. So our bag problem, two things, two problems. So we know it's a bag problem. So we need to figure out two things. We need to figure out n. N is the number of possible items that can go in a position. And that's going to be 4, because there are 4 people. And then we need to figure out how many positions there are, how many items we're taking out of the bag. So what's in the bag and how large is the bag? That's n. And then r is the number of times we're selecting from the bag, and we're giving out 2 prizes. So that's 2. Okay, so at this point, the list is of length 2. And the set is A, B, C, D. Those are the items that are in the bag. All right. So then, if you're thinking about this algorithmically, then you've identified it's a bag problem. You figured out n and you figured out r, and so you can figure out the number of ways to the number of possible combinations for this ordered list of length 2, where we're selecting items from A, B, C, and D. And in particular, that's going to be n plus r minus 1, choose r. So n is 4, r is 2, so this ends up being 5, choose 2. Okay, so that if you're thinking about the problem in, just kind of trying to figure out what type of selection problem it is, well, you figure out it's a bag problem, and then you figure out the parameters of the bag, which are 4 and 2, and then you can figure out the answer. So the number of ways to arrange to select 2 items from a bag consisting of 4 items where repetition allowed is 10. And if you, so that's the answer to the problem, but there's another way to think about this problem, which is A is allowed, B is allowed, C is allowed, and D is allowed. Those are all the repeats. There's 4 of them. There are 4 repeats corresponding to giving the prize, giving both prizes to one person. And then there is the ways that we can give one prize to one person and one prize to another person, and that would be 4 choose 2. So so it's 4 choose 2 plus 4, which is the same thing as 5 choose 2. All right, are there any questions about this one? All right. I mean, all right, yeah, if you have any questions, just shout them out. Here's the next one. All right, does anyone have any ideas for part A? Okay, so there are 26 cards in the deck, in a standard deck, that are red. And we're picking 5 cards. And we want to know how many lineups are there in which all 5 cards are red. So originally, on the first choice, there are 26 possibilities. On the second, so once we pick out a red card, then there are only 25 possibilities left over. So the second choice, we only have 25 possibilities. Then it goes on like that 5 times. So after you've chosen 2 red cards from the deck, then in order to, the number of possible ways to choose a red card now is only 24. And it goes on like this. So after we've chosen 3 red cards from a deck, there are only 23 red cards remaining. So the number of ways to choose a red card is 23, and so on. So, and in the language of the definitions that Dr. Cohen is using, this type of choosing, the order does matter. This is because we want the total number of ways to select 5 to select 5 red cards. Selecting a red king first and then a red spade would be a different combination than selecting a red spade before a red king. And we want to count all the combinations. So, so order matters. And then the other one is that repetition is clearly not allowed. So once we've chosen an item, we can't choose it again. So once we've chosen a red card, we're not going to choose that card again. Just so this type of counting is called, or just to write down the conditions here, the order matters. Okay, and then the repetition is not allowed. Yeah, oh, wait. Why is 21 there? 1, 2, 3, 4, 5, 6. Yes, that's right. Thank you. Yeah, there shouldn't be a 21 there. Repetition is not allowed. Okay. So this is, I think the word is a permutation. Okay. So the next, are there any questions about this one? Oh. Actually, I think the terminology is an ordered list. Is it, James? Is it, what is the term used for this scenario?
Just you're right. It's a permutation.
Oh, okay.
An ordered list is when repetition is allowed and order matters.
Okay. All right. Okay, the next one. So how many such lineups are there that have at least 1 red card? So there are a couple of ways to do this. One is that, well, we could count up all of the ways to get exactly 1 red card, count up all the ways to get exactly 2 red cards, and do the same thing for 3, 4, and 5. But that would be annoying. It would be kind of painful. It would take a little while. So there's another way to think about this one. So here's a set X, and X consists of all of the possible ways to select 5 cards. So for example, if so a point in X, let's call it T, it would be this 5 cards selected in a particular order, C1, C2, C3, C4, C5. So this is 5 cards in the deck where we picked, C1 was the first card we picked, C2 was the second card, and so on. So T is a element of X, and so it's a point in here. And so X consists of all of the ways to choose 5 cards. So C1, C2, C3, C4, and C5 is just one way to do this, but there are many different ways to do this. In fact, we can count up the number of points in X. So there are 52 choices for the first card. There are 51 choices for the second, 50 choices for the third, 49 for the fourth, and 48 for the last one. So in total, the size of X, or the cardinality, or I think you guys use N, and N of X is equal to 52, or actually, I remember now you guys use this notation, 52, 5. So there are this many elements in X, where X consists of all of the ways to choose 5 cards from this deck. Then if we want to count up how many lineups there are that have at least 1 card, now we should recognize that, what is that before the P? Oh, sorry, that is a scribble. There's nothing there. Sorry. So the number of points in this set X is P52, 5, which is the number of ways to, it's a permutation of the first, it's just 52 times 51 times, let me just write it out. That's 40. All right. Okay. So now we're going to use that the opposite of having at least 1 red card is having no red cards. So if we let this, here's a set, and this is the set of points in this space X where at least one of the cards is red. So let's just denote this by set R. And we want to know what the size of set R is. How many points are in set R? So instead of computing directly the number of points in set R, we're going to compute the size of its complement. Its complement is the number of cards where all the cards are not red, all the cards are black. The number of ways to choose 5 cards, to grab 5 cards where all the cards are black, is the same as part A, the number of ways to choose 5 cards where all the cards are red. So that means that for part B, we have the size of X, and we want the size of R. So so N of R, the size of R, is equal to the size of X minus the size of R complement, or X without R, or I think this is the notation used. So, all right, and we know this. This is just the answer to part A. So that's just P26, 5. And then we know this. That's the total number of ways to grab 5 cards from a deck of 52 cards, which is this down here. P52 5, which is just this 52 times 51 times 50 times 49 times 48. So 1, 2, 3, 4, 5. Yep. So this is the answer to part B. So the strategy being used here is finding the complement of the event of interest, because it would be annoying to compute the number of choices of 5 cards where the exactly 1 was red, where exactly 2 was red, where exactly 3 was red, where exactly 4 was red, and where exactly 5 was red. That would be annoying. So instead, we find the complement, which is the number of ways to choose 5 where they're all black. And that happened to have the same answer as part A. It was symmetric to part A. And so that's it. 26 times 51 times 50 times 49 times 48. So that would be like you're choosing one black card, or you're choosing one red card, and then you choose in any way possible. I think that would be okay. No, that's not.
No, not quite. That one ignores the ordering. So it ignores the order of the red card if you do it with the 26 first, because then it's like you've said the first card you pick is red, and we want to consider all possibilities where that red card could be.
All right. Okay. So that's that. The next one is how many such lineups are there for which all cards are the same suit. There are 4 suits. Each one has 13 cards in it. And so if the number of ways to choose 5 from one suit, let's just say it's the spades, would be 13 times 12 times 11 times 10 times 9. So that's just P of 13, 5. But then there are 4 suits. So it's just 4 times this. Okay. All right. That's part C. So again, we're just we have 5 cards that we're selecting to get them all from the spades. We have 13 options, then 12, then 11, then 10, then 9. But there are 4 different ways to choose from the same suit. So we have to multiply by 4. All right, and then the last one. So let me erase some stuff. Again, it's useful to draw a picture of X. So X is the same thing as it was before. And we've got 2 sets. Oh boy, that shouldn't be like that. And then let's just call the sets A and B. So A is going to be the subset of X where all 5 cards are red, and B is going to be the subset of X which is where all the cards are of the same suit. And then we want to count up the size of A union B, which is the choices of 5 where all are red, all are the same suit, or both. So to do that, we can count up the size of A and then count up the size of B, but that wouldn't be sufficient because what we would do is double count the intersection. So we just have to subtract away the intersection after we add the size of A and B. So this is called the inclusion-exclusion principle that we saw earlier in the course. this is going to be n of A plus n of B minus n of A intersection B. Oops, A intersection B. Okay. So, so luckily we already found n of A and n of B. N of A was this answer, and it was the number of ways to choose 5 red cards. N of B was this answer. No, sorry, N of B was this answer. The number of ways to choose cards all from the same suit. So then the only thing we have to do is subtract away the intersection. So we have to subtract away all of the combinations or all of the selections of cards where the cards are all red and they're of the same suit. And here there are, if you remember from a deck of cards, there are 2 suits that have a red color. So we have to subtract away all of the ways to select to select 5 cards from one of those 2 suits, that are red. So each suit has 13 cards, and so selecting from all from the same suit from one of those suits, let's just say that the red suit is one of the red suits is the kings, then selecting 5 cards from the kings in succession is P of 13, 5. And then there's some other set that's red, maybe it's the spades. So selecting 5 from that suit would be P 13, 5. And so the size of the intersection is 2 times P 13, 5. And that's it. So we already did the answer to part A and part C. So part A gives this one, and part C gives this one, and 2 times P 13, 5 gives that. So we have part D. So that's it. At 2 p.m., James has his office hours. So have a great weekend. And yeah.